Have you ever tried to scan a broken QR code? It works instantly, even if it is completely ruined. This is not magic. It is pure mathematical brilliance. Have you ever been at one of those outdoor cafes on a windy day, squinting at a menu that's basically just a weathered QR code sticker slapped onto a metal table? It's probably scratched, faded by the sun, and partially obscured by olive oil. You point your phone at it, expecting an error, but then, ding, the digital menu pops up. Or think about those massive billboards, where a brand's giant logo sits right in the center, obliterating a huge chunk of the data points. By all laws, that code should be dead. Yet it works every single time with surgical precision. It feels like a miracle. But in engineering, miracles are just very clever math. Today, I want to take you behind the curtain to see how these pixels manage to survive such deadly damage. To understand why a mangled square can still function, we first have to redefine what broken actually means to a computer. In a traditional barcode, data is read in a single line. If one part is gone, the whole sequence is ruined. But the QR code was built for a much rougher life. It has a built-in safety net known as error correction, the armor of the digital world. Let's try a little thought experiment. Imagine you're at a deafeningly loud rock concert, and you're trying to shout your phone number. If you just yell the digits once, the kick drum or a scream from the crowd will likely swallow half the numbers. So, what's your natural instinct? You don't just say it once. You repeat yourself. You shout the number again and again to be safe. You are providing redundancy. You're giving your friend extra backup information so their brain can piece the whole sequence together. QR codes do exactly that, but with a mathematical weapon called the Reed-Solomon error correction algorithm. You might recognize that name. It's the same heavy-duty math NASA used to beam photos back from deep space, and it's what allows scratched Blu-rays to play. Instead of just storing a link, the algorithm calculates extra parity data. Think of them as mathematical echoes of the original message. But here's the brilliant part. The software doesn't just dump this backup data in a heap. It weaves it across the entire grid. It's like a hologram. If you break off a piece of a hologram, the whole image is still encoded in the remaining fragments. So, when your camera hits that stain, it isn't just seeing a picture. It's performing high-speed calculus in the palm of your hand. It identifies which squares are impossible, ignores them, and uses the backup pieces to reconstruct the original message in milliseconds. It literally heals itself. But how much damage can it take? Well, that depends on the 4 levels of toughness. L, M, Q, and H. Level L is the light version, surviving about 7% damage. Great for clean digital displays. Level M handles a 15% loss. Then we have level Q at 25%. And finally, level H, the absolute tank. It can lose a staggering 30% of its surface and still scan perfectly. Why not use level H for everything? Well, more backup data means more little squares. It makes the code look incredibly dense and busy. On a tiny business card, a level H code might become such a crowded mess that the ink bleeds, making it even harder to scan. This armor is why those codes with a logo in the center work. The designer isn't hacking, they are using error correction as a tool. They choose level H, knowing the logo covers maybe 15% of the data. Since the code handles 30%, there's plenty of mathematical breathing room. However, not every pixel is created equal. Look at those 3 large, double-bordered squares in the corners. These are the finder patterns. They carry zero data. They act like digital compasses, telling the scanner, "Hey, I'm a QR code, I'm tilted, and here's where I begin." If you scratch out or cover even one of those squares, the whole thing dies. The scanner loses its orientation instantly. It's the Achilles heel. What about a code wrapped around a curved soda bottle or crumpled on a box? Error correction helps, but there's another hero for geometry. These are alignment patterns. They act as reference points, telling the software how to digitally stretch and flatten a distorted image. This toughness was a deliberate choice. Back in 1994, a Japanese engineer named Masahiro Hara was tasked with improving part tracking for Toyota. In a car factory, things are messy. Traditional barcodes were constantly failing because of grease, oil, or scratches stopping production lines. Inspired by the game of Go, Hara designed a system that traded a bit of space for incredible ruggedness. He built in redundancy on purpose. He wanted a robot to read a filthy, battered label on a car engine in the middle of a noisy factory. And it worked. So, next time you casually scan a crumpled, coffee-stained code, take a second to appreciate the heavy-duty space math. It's a 30-year-old invention that still feels like the future because it was built to survive the real, messy world. If you enjoyed this journey, hit that like button and subscribe to Amazing Nearby. Share this with a friend. Stay curious. I hope you enjoyed this journey into the simple things. Keep exploring, and I'll see you in the next one. Take care.